Hello, welcome to the video lecture series on digital image processing. For last few classes, we were discussing about restoration of blurred images. So, what we have done in our last class is estimation of degradation models. We have seen that whatever restoration technique we use, the restoration techniques mainly use the knowledge, a priori knowledge of the degradation model which degrades the image. So, estimation of the degradation model degrading an image is very important for the restoration operation. So, in our last class, we have seen three methods for estimation of the degradation model. The first method we discussed is the estimation of the degradation model by observation. The second technique that we have discussed is the estimation by experimentation, and the third technique that we have discussed is the mathematical modeling of degradation. Then we have also seen what should be the corresponding restoration technique, and in our last class we have talked about the inverse filtering technique, and today we will talk about the other restoration techniques which also makes use of the estimated degradation model or the estimated degradation function. So, in today's lecture we will see the inverse filtering, the restoration of the motion blurred image using the inverse filtering technique. In our last class we have seen inverse filtering technique where the image was degraded by turbulence, atmospheric turbulence model. We will also talk about the minimum mean square error or Wiener filtering approach for restoration of a degraded image. We will also talk about another technique called constant least square filter, where the constant least square filter mainly uses the mean and standard deviation of the noise which contaminates the image, the degraded image. And then we will also talk about the restoration techniques where the noise present in the image is a periodic noise. So, firstly, let us quickly go through what we have done in our last class. So, we are talking about the estimation of the degradation model, because that is a very basic requirement for the restoration operation. So, the first one that we have said is the estimation of the degradation model by observation. So, in this case what is given to us is the degraded model, and by looking at the degraded model we have to estimate that what is the degradation function. From the degraded image we have to estimate what is the degradation function. So, here we have shown one such degraded image, and we have said that once a degraded image is given, we have to look for a part of the image which contains some simpler structure, and at the same time the energy content, the signal energy content in that part, in that sub image should be very high to reduce the effect of the noise. So, if you look at this particular degraded picture, you find that this red rectangle, it shows an image region in this degraded image which contains a simple structure, and from this it appears that there is a rectangular figure present in this part of the image. And there are two distinct gray levels. One is of the object which is towards the black, and other one is the background which is a grayish background. So, by having a small sub image from this portion, what I do is I try to manually estimate that what should be the corresponding original image. So, as shown in this slide, the top part is the degraded image which is cut out from the image that we have just shown, and the bottom part is the estimated original image. Now, what we do is from this, if you take the Fourier transform of the top one, what I get is the GUV, as we said that it is the Fourier transformation of the degraded image, and the lower one we are assuming this to be original, So, if I take the Fourier transform of this, what I get is f u v, that is the Fourier transform of the original image. And obviously, here the degradation model or the degradation function in the Fourier domain is given by h u v, which is equal to g u v by f u v. And you remember that in this case the division operation has to be done point by point. So, this is how the degradation function can be estimated by observation when only the degraded image is available. The other approach for estimation of the degradation function we have said is the estimation by experimentation. So, our requirement is that whichever imaging device or imaging setup that has been used for getting a degraded image, which has been used to record a degraded image, in our laboratory for experimentation purpose, we will have a similar such imaging setup. And then we try to find out that what is the impulse response of that imaging setup. As we have already discussed, that it is the impulse response which completely characterizes any system. So, if we know what is the impulse response of the system, we can identify, we can always calculate what is the response of the system to any type of input signal. So, by experimentation, what we have done is we have taken a similar imaging setup and then you simulate an impulse by using a very narrow strong beam of light. So, as has been shown in this particular diagram. So, on the left hand side, what is shown is one such simulated impulse in this particular diagram. So, the left hand side, this one shows such simulated impulse, and on the right hand side what we have is the response of this impulse as recorded by the imaging device. So, now if I take the Fourier transform of this, this is going to give me f u v, and if I take the Fourier transform of this, this is going to give me g u v. And you see that because the input, the original is an impulse, the Fourier transform of an impulse is a constant. So, if I simply take the Fourier transform of the response, which is the impulse response, or in this case it is the point spread function, then this divided by the corresponding constant will give me the degradation function, which is h u v. So, this is how we estimate the degradation function of or the degradation model of the imaging setup through experiment. The third approach for obtaining the degradation model is by mathematical modeling. So, in our last class we have considered two such mathematical models. The first mathematical model that we have considered, which tried to give the degradation function corresponding to atmospheric turbulence, and the function is given, the degradation function in the frequency domain is given like this, that h u v is equal to e to the power minus k u square plus v square to the power 5 by 6. And using this degradation model, we have shown that how a degraded image will look like. So, in this particular case, we have shown 4 images. Here the top image, the top left image, this is the original one, and the other 3 are the degraded image which have been obtained by using the degradation model that we have just said. Now, in that degradation model, when I said that e to the power minus k u square plus v square to the power 5 by 6, it is the constant k which tells you that what is the degree of the degradation, or what is the intensity of the disturbance. So, low value of k indicates the disturbance is very low. Similarly, higher value of k indicates that the disturbance is very high. So, here this image has been obtained with a very low value of k, this image has been obtained with a very high value of k, and this image has been obtained with a medium value of k. So, you find that depending upon the value of k, how the degradation of the original image changes. The second mathematical approach that, or the second model that we have considered is motion blurred or the blurring which is introduced due to motion. And we have said that because the camera shutter is kept open for a finite duration of time, the intensity which is obtained at any point on the imaging sensor is not really coming from a single point of the scene, but the intensity at any point on the sensor is actually the integration of the intensities or light intensities which are falling to that particular point from different points of the moving object, and this integration has to be taken over the duration during which the camera shutter remains on. So, using that concept, what we have got is a motion mathematical model for motion blur, which in our last class we have derived that it is given by h u v equal to integration 0 to t e to the power minus j 2 pi u x naught t plus v y naught t dt, where this x naught is the movement, this x naught t indicates movement along x direction and y naught t indicates movement along the y direction. So, if I assume that x naught t is equal to a and y naught t equal to b, then this particular integral can be computed and we get a final degradation function or degradation model as given in the lower equation. And after this, in our last class what we have done is we have used the inverse filtering, and using this motion blurring model, this is the kind of blurring that we obtained. This is the original image. On the right hand side we have shown the motion blurred image. Then we have seen that once you have the model for the blurring operation, then you can employ inverse filtering to restore a blurred image. So, in your last class we have used the inverse filtering to restore the images which are blurred by atmospheric turbulence. And here again on the left hand side of the top row we have shown the original image. So, this is the original image, this is the degraded image, and we have said in the last class, because by inverse filtering the function, the blurring function h u v comes in the denominator. So, if the value of h u v is very low, then g u v upon h u v, that particular term becomes very high. So, if I consider all the frequency components or all values of u v in h u v for inverse filtering, the result may not be always good, and that is what has been demonstrated here, that this image was reconstructed considering all values of u and v, and you find that this fully reconstructed image does not contain the information that we want. So, what we have to do is, along with this inverse filtering, we have to employ some sort of low pass filtering operation, so that the higher frequency components or the higher values of u and v will not be considered for the reconstruction purpose. So, here on the bottom row, the leftmost image, this shows the reconstructed image, where we have considered only the values of u and v which are within a radius of 10 from the center of the frequency plane. And because this is a low pass filtering operation where the cutoff frequency was very low, so the reconstructed image is again very blurred, because many of the low frequency components along with the high frequency components have also been cut out. The middle image shows to some extent a very good image, where there is distance within which u v values were considered for the reconstruction were taken to be 40. So, here you find that this reconstructed image, this contains most of the information which was contained in the original image. So, this is a fairly good restoration. Now, if I increase the distance function, the value of the distance, if I go to 80, that means many of the high frequency components also we are going to incorporate while restoration. And you find that the rightmost image on the bottom row, that is this one, where the value of the distance was equal to 80, this is also an reconstructed image, but it appears that the image is behind a curtain of noise. So, this clearly indicates that if I go on increasing or if I take more and more u and v values, the frequency components for restoration using inverse filtering, then the restored image quality is going to be degraded. It is likely to be dominated by the noise components present in the image. Now, though this inverse filtering operation works fine for this turbulence kind of blurring, the blurring introduced by the atmospheric turbulence, but this direct inverse filtering does not give good result in case of motion blur. So, you find that here we have shown the result of direct inverse filtering in case of motion blur. So, on the topmost one, this is the original image. On the left, we have shown the degraded image, and the rightmost one on the bottom is the image, restored image obtained using the inverse, direct inverse filtering, and the blurring which was considered in this particular case is the motion blur. Now, let us see why this direct inverse filtering does not give satisfactory result in case of motion blur. The reason is, if you look at the degradation function, the motion degradation function, say for example, in this particular case, you find that the degradation function h u v is given by this expression in the frequency domain. Now, this term will be equal to 0 whenever this component u a plus v b, this is going to be integer. So, for any integer value of u a plus v b, the h u v, the corresponding component h u v will be equal to 0. And for nearly integer values of this u a plus v b term, h u v is going to be very, very low. So, about direct inverse filtering, when we go for dividing g u v by h u v to have the Fourier transformation of the reconstructed image, wherever h u v is very low, near about 0, the corresponding f u v term will be abnormally high. And when you take the inverse Fourier transform of this, that very, very high value is reflected in the reconstructed image, and that is what gives to a reconstructed image as shown in this form. So, what is the way out? Can't we use the inverse filtering for restoration of motion blurred image? So, we have attempted a roundabout approach. What we have done is, again we have taken an impulse, try to find out what will be the point spread function of if I employ this kind of motion blur. So, by using the same motion blur function or the motion blur model, you blur this impulse, and what I get is an impulse response like this, which is the point spread function in this particular case. Now, once I have this point spread function, then as before, what I do is I take the Fourier transform of this, and this Fourier transformation now gives me g u v, and because my input was an impulse, where so for this impulse f u v is equal to constant, which is a something like a. Now, from these two I can recompute h u v, which is given by g u v divided by this constant term a. Obviously, the value of constant is same as what is the intensity of this impulse. So, if it is an unit impulse, if I take an unit impulse, then the value of constant a will be equal to 1, and in that case the Fourier transform of the point spread function directly gives me the degradation function h u v. Now, if I perform the inverse filtering using this recomputed degradation function, then we find that the reconstruction result is very, very good. So, this was the blurred image, this is the reconstructed image during by using the inverse filtering, direct inverse filtering, but here the degradation model was recomputed from the point spread, from the Fourier transformation of the point spread function. So, though using the direct inverse transform of the mathematical model of the motion blur does not give me good result, but recomputation of that degradation function gives a satisfactory result. But again, with this inverse filtering approach, the major problem is, as we said, that we have to consider the UV values for reconstruction, which is within a limited domain. Now, how do we say that up to what extent of UV value we should go? That is again image dependent. So, it is not very easy to decide that to what extent of frequency components we should consider for the reconstruction of the original image if I go for direct inverse filtering. So, there is another approach which is the minimum mean square error approach, or it is also called the Wiener filtering approach. In case of Wiener filtering approach, the Wiener filtering tries to reconstruct the degraded image by minimizing an error function. So, it is something like this. So, if my original image is f and my reconstructed image is f hat, then the Wiener filtering tries to minimize the error function, which is given by expectation value of f minus f hat square. So, the error value E, which is given by the expectation value of f minus f hat square, where f is the original degraded image and f hat is the restored image from the degraded image. So, f minus f hat square, this gives you the square error, and this Wiener filtering tries to minimize the expectation value of this error. Now, here our assumption is that the image intensity and the noise intensity are uncorrelated, and using that particular assumption, this Wiener filtering works. So, here we will not go into the mathematical details of the derivation, but it can be shown that a frequency domain solution of this, I mean whenever this error function is minimum, the corresponding f u v in frequency domain is given by f hat u v. This will be equal to h star u v into s f u v divided by s f u v into h u v square plus s eta u v, this into g u v, where this h star indicates it is the complex conjugate of h u v, and g u v as before it is the Fourier transform of the degraded image, and f hat u v is the Fourier transform of the reconstructed image. And in this particular case, this term S f u v, this is the power spectrum of original image, undegraded image, and S eta u v is the noise power spectrum. Now, if I simplify this particular expression, I get an expression of this form, that f hat u v is equal to 1 upon h u v into h uv square upon h u v square plus s eta u v upon s f u v into g u v. So, this is the expression of the Fourier transform of the reconstructed image when I use Wiener filtering. Now, in this case you might notice that if the image does not contain any noise, then obviously S eta u v, which is the power spectrum of the noise, will be equal to 0, and in that case this Wiener filter becomes identical with the inverse filter. But if the noise contains additive noise, if the degraded image also contains additive noise in addition to the blurring, in that case the Wiener filter and the inverse filter is different. Now, here you find that this Wiener filter considers the ratio of the power spectrum of the noise power of the noise power and the power of the power spectrum of the original undegraded image. Now, even if I assume that the additive noise which is contained in the degraded image is a white noise for which the noise power spectrum will be constant, but it is not possible to find out what is the power spectrum of the original undegraded image. So, for that purpose what is done is, normally this ratio, that is S eta u v upon S f u v, that is the ratio of the power spectrum of the noise to the power spectrum of the original undegraded image, is taken to be a constant k. So, if I do this, in that case the expression for f hat u v comes out to be 1 upon h u v into h u v square upon h u v square plus k into g u v. So, where this k, the term k is a constant which has to be adjusted manually for the optimum reconstruction, or for the reconstructed image which appears to be visually best. So, using this expression, let us see what kind of image that, or what kind of reconstructed image that we get. So, here we have shown the image restoration of the degraded image using Wiener filter. Again, on the left hand side of the top row it is the original image, right hand side of the top row gives you the degraded image, leftmost image on the bottom row, that shows you the full reconstructed image, or the reconstructed image using the inverse filtering, where all the frequency components are considered. The middle one shows the reconstructed image using inverse filtering, where only the frequency components within a distance of 40 from the center of the frequency plane has been considered for reconstruction, and the rightmost one is the one which is obtained using Wiener filtering, and for obtaining this particular reconstructed image the value of k was manually adjusted for best appearance. Now, if you compare these two, that is the inverse filtered image with the distance equal to 40 with the Wiener filtered image, you will find that the reconstructed images are more or less same, but if you look very closely, it may be found that the Wiener filtered image is slightly better than the inverse filtered image. However, visually they appear to be almost same. The advantage in case of Wiener filter is that I do not have to decide that what extent of frequency components I have to consider for reconstruction or for restoration of the undegraded image. But still the Wiener filter has got a disadvantage, that is the manual adjustment of the value of k, and as we have said that the value of k has been used for simplification of the expression, where this constant k is nothing but a ratio of the power spectrum of the noise to the power spectrum of the undegraded original image. And in all the cases, taking this ratio to be a constant may not be a justified approach. Thank you.